Welcome to tonight's webinar featuring Mike Hershberg introducing Dr. David Coleman. I wanted to introduce myself first. My name is Elizabeth Ward, and I'm one of the co-presidents for the Southwest chapter of VFS. I am joined here, he's hiding right now, by Nathan, who might be our co-president, and we have a few other people attending who are on our leadership board as well, and I want to thank them for being here. From a Southwest chapter perspective, I do want to put out that we have a lifting competition and submissions are due November 19th. So if you are interested in the lifting competition, that's for people who have never presented at a major forum or conference before. There is a monetary prize for the winner. And we'd love to see some of those papers come in. So again, if you are interested in joining the lifting competition, those papers are due, or I believe the abstracts are due November 19th. If you have any questions at all during this webinar, please feel free to enter them into the chat section on the right-hand side of your screen. We are not going to be taking questions during the presentation itself. So again, if you do have any questions, we'll get to those at the end. And please feel free to add your questions and we'll go through them at the very end. You're also more than welcome to send me a private question if you don't want it to be a public question that pops up for everybody. And with that, I am going to go ahead and introduce our introducing speaker, Mike Hershberg. I don't really have a long introduction for him. He's kind of self-explanatory. Mike has been the executive director of VFS since 2011. So he's been in that role for over a decade now. And so we're very thankful for him to join us this evening. And so Mike, I'm just gonna go ahead and hand it off to you. Thanks.
Excellent. Thanks, Elizabeth. And I was talking with Elizabeth last week in preparation for this, and I know everybody's really busy. It's an incredible time in the vertical flight industry with the future vertical lift and electric VTOL and commercial programs and so much in innovative technologies. And I know a lot of employers are really short-staffed, trying to hire more people. People are working long hours, and I really appreciate everybody, first of all, coming out tonight for this event, and we're gonna have a great speaker. And also to people like Elizabeth and Nathan who've said, in addition to the long hours I'm working at work, I'm also going to do this extra thing, which I don't have to. I got enough stuff going on in my life, but I'm going to do it. And look, you guys turned out. And as I say often, if everybody does a little bit, it'll add up to a lot. And it's a really great thing when we have this opportunity to learn from each other and network and help advance vertical flight. So kudos to the officers and everybody who's turned out tonight. So I'm very pleased to introduce tonight's speaker, David Coleman, who just earned his PhD from the Department of Aerospace Engineering at Texas A&M University, where he is a member of the Advanced Vertical Flight Laboratory. But first, I'm going to give a couple remarks on VFS and the GoFly prize, which he'll be speaking on. So next chart, Chris. So I think everybody here probably knows what VFS is, but if you don't, or if any of this is news to you, we're up to 6,500 individual members. We also have 160 corporate members, so we've really been growing over the last several years. We were started as the American Helicopter Society. We went by AHS International from 1997 to 2018, 20 years. Trying to say we're not just American, we're not just helicopters, we're everything. But really with the explosion of interest in drones and eVTOL and other rotorcraft, we really decided not that we wanted to change our name because we wanted to become something else, but we were already the Vertical Flight Society, and we just needed to change the name to reflect who we really were and who we really are. So we're a nonprofit, we're a charitable organization. Our whole reason to exist is to expand knowledge, advance vertical flight, and help not only create new technologies and capabilities, but to field them, to get them out into the field for the improvement of society. And obviously, if you're not a VFS member, but you're in vertical flight, please join us at vtol.org. Next. So, we've now been around we've got Forum 78 coming up in Fort Worth in May. We're very excited about that. We've got, 8 decades of experience working to support you guys, to support the vertical flight industry, working with the government, working with companies, academia, to do the great things that will help advance vertical flight. And again, it's not just helicopters. I'm here today because in 1995, I was working with the JAS program office, and they had a Stovall aircraft, and the American Helicopter Society, reached out and joined with the JSF office, and they needed help, and VFS AHS at the time helped support the program. And today we've got supersonic Stovall strike fighter, so pretty impressive work that the vertical flight community, the larger vertical flight community, gave birth to. And I think as far as a tilt rotor, probably no other organization besides Bell, Boeing, and the U.S. Marine Corps has been a bigger supporter of tilt rotors. So we're very pleased at the role that we've been able to provide, and now tilt rotors are becoming more of a mainstream aircraft. Under my tenure, or just prior to my tenure, in 2008, we started supporting what's now the Future Vertical Lift program, and since 2013, I've been supporting the eVTOL world. So we look for things that are going to be that, we're a small organization, but we're harnessing your energy and your enthusiasm and your knowledge to advance vertical flight, and we look for those areas where we can provide a tipping point. Next slide. So again, we were founded in 1943. Our very first awards banquet is in 1944. 70 years later, we had the world's first eVTOL workshop. It was a limited space. It was 100 people. And on that front row, you guys might not recognize them, but there's some really leaders in the eVTOL industry today, and actually throughout the whole audience there. Next chart. So one of the things that so we had our second one in August of 2015, a year later, and at that meeting, Gwen Leiter presented this crazy idea of what was called at the time GoFly Up, which was a competition for a small personal flying device. It took a few years before she worked out the details. We used a lot of VFS members to help come up with the criteria and try to get sponsors for it. Eventually, Boeing did pick up the primary sponsorship for that. Next. This is the subject of David's talk, so he'll go through this in detail. But it was a $2 million, actually a little bit more than $2 million competition to develop a personal flying device. You see some of the numbers here. And things, any one of these or any 2 or 3 of these would be, challenging, but to do them all within one aircraft, to have it so small, quiet, have a speed, an endurance, a range, all these things, and carrying a human pilot or human passenger was just really, at the edge of possibility. Next chart. They got a lot of interest. They awarded 10 awards in 2018 for $20,000 a piece. Next chart. And then there is a phase 2. And it wasn't a down select, so this is basically encouragement money for teams that had been submitting designs. And one of the few designs that were on both the first and second was the Harmony, supported by Texas A&M University. You see it over in there on the right. And of course, we're helicopter people, so of course you need a big rotor, right? And if you're volume constrained like that, you need the biggest rotor you can. You need to stick the person in there. So you got to wonder, if you're not a helicopter person, where these other people got these ideas. But we'll get to that. So next chart. On Leap Day, right before COVID hit bad, I was flying around the West Coast a lot, January and February of this year, through a lot of airports. But kind of one of the last, the big hurrahs for the vertical flight industry was the final fly off. You see there next to Hangar 1 at Ames at Moffett Field. This is a display tent area. Next chart. You know, on our websites, we have, over the course of several years, 6 in-depth articles, a couple other articles on GoFly. You can look at our eVTOL.news site. At the fly-off itself, we have over 150 pictures of the different companies. Because of the pandemic, you know, they weren't going to have another fly-off, and basically, you know, when somebody's ready to try and meet the challenge, then they'll go out there and they'll do a test, or they'll do the evaluation to see if they meet the requirements. So next chart, GoFlyPrize.com is a website. Here's some of our pictures we had of the Harmony team on that day. Next chart. And so we're going to have this talk now from David on what his team did and the experience there. As I mentioned, he was at Texas A&M. During his time there, he worked on the design and development of several novel vertical flight concepts, including a hover-capable robotic hummingbird, you see there on the right, cyclocopters, other rotary-wing based aircraft. I met David in 2015 when he won one of our VFF scholarships as a master's student, and of course I was very impressed. You see some of the other prizes, Licton Best Paper Award. He also won another VFF scholarship in 2018. He's actually been the author on 3 best papers at the forum, including this past year. And of course, we're here today to hear about the electric helicopter that he and his advisor, Dr. Mobile Benedict, who we're happy to have here, and his other lab mates developed for the GoFly's competition and his future plans. So, David, over to you.
Thanks, Mike. Let me get the screen share here going.
Just gave you the presenter role, David.
All right, excellent. Can you all see the PowerPoint now? I just pulled up the slide.
Yeah, we can.
Okay, excellent, excellent. All right, well, good evening, all. I appreciate that introduction, Mr. Hershberg, and I want to thank, of course, the VFS Southwest chapter for their support and for allowing me to present this project. I am Dr. David Coleman, graduate research assistant here at Texas A&M University, and I will be discussing the development of an aircraft called Aria, a compact, ultra-quiet personal electric helicopter. I had the opportunity to develop this aircraft with my advisor, Dr. Mobile Benedict, as well as several lab mates, postdocs, external members, and stuff. So I'll just talk briefly about the GoFly competition and some of the constraints, and then some of the technologies that we developed in an effort to address those, and as a result of our participation therein. So let me see if I can advance here. Okay, so I'll talk about, just give an overview of the competition, the motivation behind the project. I'll discuss this particular aircraft configuration that we selected and why we did. I'll discuss some historical coaxial personal helicopters, and then the design and development of some of the key subsystems in our aircraft. And so I'll talk about flight testing, both the subscale aircraft, which was a 1/3 scale, and then also the full-scale aircraft as well. And then we'll conclude with some lessons learned. So the GoFly competition, it was an initiative to foster the development of safe, quiet, ultra-compact VTOL aircraft for carrying a single person for a range of about 20 miles. And so, as we mentioned, the $2 million X-prize sponsored by Boeing. 3 phases. The first phase was a white paper design, and this was due in April of 2018. 10 winners were selected, each of them awarded $20,000. And then phase 2 was the development and flight testing of a subscale prototype, and this occurred in February of 2019. 5 winners were selected, each of them awarded $50,000. And then the final phase is a fly-off demonstration of a full-scale aircraft. It's an ongoing, and if any of the competitors are able to meet the competition constraints, then of course they'll be the winner and awarded the $1 million. So what are some of these competition constraints? What are some of these scoring metrics? Well, there was 3 basic: size, noise, and speed. And the important thing here is that if you look at the y-axis, you can see that the size and the noise were weighed a lot more heavily than the speed. And so we focused a lot on those two in the development of our aircraft. Now, of course, there were other performance requirements, including aircraft had to complete 6 laps around two pylons located a half nautical mile apart. There were also endurance requirements, including 20 minutes of total flight time with an additional 10 minutes of reserve. And then the competition really emphasized an open air flight experience. So this required the operator to have an unobstructed 90-degree field of view at all times. And so Team Harmony, as was known, was formed to create solutions and develop a really competitive eVTOL aircraft using as rigorous and scientific an approach as possible. And so, as Mike mentioned, we were one of 10 phase 1 winners. Out of over 1,300 global competitors, we're one of 5 phase 2 winners for our subscale prototype. And of course, we went on to develop and flight test a full-scale prototype for phase 3. And so this talk is going to be mostly discussing the design and development of these 2 aircraft. So how did we determine our particular aircraft configuration? Well, we considered several options. We looked at more conventional configurations, such as a single main rotor or a tandem rotor, intermeshing, or even a compound helicopter configuration. And these we just determined are not the most compact solution. A lot of them suffer from tail rotor noise as well. We also looked at ducted rotors and jetpacks. Now, these are a lot more compact, but they suffer from excessive noise and extremely low efficiency. We also looked at reconfigurable aircraft like tilt rotors, tilt wings, and tail sitters. And for the purposes of our mission, this was just too mechanically complex and required a lot of inconvenient reorientation. Now, we also considered multicopters, which is a pretty popular choice amongst eVTOL developers today. Now, even multicopters, they're not the best choice for both maximizing aircraft efficiency as well as minimizing noise. In fact, in order to do this, there's 2 fundamental requirements. Is 1, you got to minimize disk loading, and number 2, you have to minimize blade tip speed. And so after considering all of these, we determined that the optimal solution for this problem was a coaxial rotor system with an 8.5-foot diameter. This is very near the maximum size that was allowed in the competition. And so if we just compare this, let's say, to a quad rotor configuration, again with an 8.5-foot diameter, there's a myriad of advantages to the coaxial configuration, including over 4 times more disk area, which results in significantly lower power per unit thrust. The large rotors will operate at much higher and more efficient Reynolds numbers. And the design of the coaxial system is just a lot safer and more optimal use of space, since the pilot is at the center where the rotor speed is the lowest and you're really not generating much thrust anyway. And then there's also numerous acoustic benefits to the coaxial configuration. And in order to truly understand these and appreciate these, we need to look at helicopter noise generation mechanisms. And these come from a variety of different sources, including thickness noise, you've got steady loading noise, high-speed impulsive noise. And the fortunate thing is that all of these can be mitigated pretty effectively through tip speed reduction. Now, you also have other noise sources such as broadband noise and unsteady loading noise. Unfortunately, these are relatively insensitive to any type of tip speed reduction efforts, and so these have to be addressed in different ways. So I'll be discussing some of these throughout the talk. Now, another important consideration is A-weighting acoustics. Now, this is just a variation in perceived loudness of sound as a function of frequency as sensed by the human auditory system, by the human ear. And that's pretty clear, seen in this graph of decibel level versus frequency. You can see that for a reference tone, the lower frequencies are generally perceived as quieter, while those in the higher range, particularly in the 1 to 5 kilohertz, are really perceived as much louder than they are. And so this is one reason why things like a quad rotor or maybe a chainsaw are particularly loud and irritating, because your ear is kind of naturally amplifying the frequency range in that particular frequency range. So from an acoustic standpoint, if we just compare the coaxial configuration versus a quad rotor, there's a couple things to keep in mind. Is first, the magnitude is going to be a strong function of blade tip speed, and then the frequency of the sound, which is basically the blade passage frequency, is going to be a function of two things: your RPM and the number of blades. So if we just put these in a chart side by side, in the case of the coaxial system, we've got a large rotor operating at low tip speed, so we get a pretty low noise magnitude. But then in the case of the quad rotor, we have the opposite. We've got small rotors, high tip speed, and the penalty is a high noise magnitude. If you look also at the low RPM of the coaxial configuration, this is going to result in a much lower frequency, and as a result, an A-weighted advantage. The opposite, again, is true with the quad rotor. You're going to suffer from high frequency and an A-weighted disadvantage. And you can see that demonstrated pretty clearly in this acoustic simulation of a coaxial system versus a thrust-matched quad rotor of the same footprint. You can see that the natural frequency and the unweighted and A-weighted sound levels of the quad rotor are higher in comparison to that of the coaxial, on the order of 25, 30 decibels. So clearly from this result, the coaxial configuration results in a much lower frequency and a much lower sound pressure level, which is really what you want for the purposes of this competition. Now, another consideration in a coaxial configuration is rotor spacing. And so we did some experiments where we measured the sound pressure levels for a variety of spacings between the coaxial system. And these results are shown here. And really, you don't really get a significant increase in sound pressure level until the distance is less than about 25% of the rotor radius. And so for compactness purposes, we wanted to keep this as small as possible. So that was the distance that we selected for our vehicle. So our final configuration consisted of a coaxial rotor system with a rotor diameter of 8.5 feet. That separation distance was 25% of the rotor radius, and we positioned the pilot above the rotor system to have a clear field of view to stay consistent with the spirit of the competition. So as I mentioned, there have been some historical coaxial PAVs developed in the past. Some well-known examples of the Aerocycle and the Hiller platform. These were developed for military purposes, and these rely on kinesthetic control. So this is where the pilot shifts their weight in order to control the CG location of the vehicle. More recently, we've got the Gen H4 and the first manned electric helicopter. Now these have the rotor system on a gimbal, and so the pilot uses manual thrust vectoring in order to control the system. So you can see in all of these cases, we get a really heavy dependence on the pilot skill, and so this prevents you from utilizing any type of stability augmentation system that'll help to enhance the flight. And so as a result, none of these are really the best choice for a personal air vehicle that's going to be flown by the average individual. And so we developed our own coaxial helicopter. And so let's talk about the design and development of that system. We'll start first with the rotor system itself. And we had several key design tools, starting with an in-house blade element momentum theory code. And this captured a lot of the complex aerodynamic interactions between the two rotors in the coaxial system. We also utilized Helios, which is a computational fluid dynamics code, and that captured the flow field and the air loads on the blades of the coaxial system. And then we had an in-house acoustic solver that modeled all of the helicopter noise generation mechanisms. And so we used these tools to do a pretty detailed parametric study, which had two basic objectives. One was to minimize forward flight power, and the second was to minimize noise and hover. And so I'll go through the different parameters that we varied, starting first with the rotor RPM. And so here you can see in this plot on the left-hand side of power versus forward speed, we can see pretty clearly that the lower RPM decreases the required power. But then we have to look over here on the right-hand side of max angle of attack versus forward speed. And clearly you can tell that the lower RPM actually increases the required angle of attack and thus decreasing stall margin. So after balancing these two, we determined that the best RPM was 950 because this gave us a reduced power requirement, but then also allowed us at least a 30% stall margin. So we also did a similar investigation for the solidity. You can see that higher solidity results in lower power requirement, but then again, the higher solidity results in higher angle of attack, decreased stall margin. So we selected a solidity of 0.2 for this rotor design. Similarly, we did the same for the taper ratio. We determined a taper ratio of 2 was the best for this configuration. And then for twist, we determined that the optimal twist was -9 degrees. Now, another thing we looked at was the number of blades. This was a little bit more interesting because we brought in acoustics to bear. So here you can see in the plot on the left, the greater the number of blades, that decreases the power requirement, but we do see that we get diminishing returns when our number of blades is greater than 4. The other thing to keep in mind also is that the more blades, this is going to necessarily increase the rotor weight and complexity. And so we looked at acoustic simulations, and here you can see in this plot of A-weighted sound levels versus tip Mach number for a series of blade design, for a series of number of blades. And we see that the greater the number of blades, this decreases our tonal noise. But then for any given number of blades, broadband noise will increase with angle of attack. And that's kind of demonstrated here. This is an indication of flow separation as the sound level increases at lower Mach numbers. Now, for our 950 RPM, we're operating at a Mach number of about 0.35, and you can see that there's a nice little valley in the acoustic simulation for the number of blades being 4, and so this was ultimately the number that we chose for our system. Now, we also had 3 basic requirements for our airfoil. We wanted high lift to reduce RPM and noise levels, high CL over CD, and of course we wanted a thin profile in order to reduce thickness noise. So we down selected to 4 key airfoils. Here you can see that in power versus forward speed, our NASA RC410 and Clark Y performed the best. And so we then took these and looked at pitching moment, and you can see that the NASA RC410 had a lower pitching moment, and so this was the airfoil that we selected. Now, we also looked at blade planform shaping, and the reason why is because in the case of coaxial rotors, they generate this impulsive noise as the blades pass over each other. That's known as blade crossover events. So in the case of straight blades, you get this instantaneous blade overlap, which results in pretty strong acoustic effects. Now, if we were to introduce some sort of double swept design, then that'll basically distribute that blade overlap over a longer period of time. And it'll essentially dephase these aerodynamic interactions, make the sound a lot softer, much more pleasant. And so that's what we did. So here you can see in this photograph of our full-scale rotor blade, we swept it forward by about 5 degrees up to the 62% radial location, and then swept it backwards 20 degrees from that point onwards. And the benefits from this is demonstrated in our acoustic simulation. We saw about a 4.4 dBA noise reduction as a result of introducing this. And so what I want to do is I want to share with you some clips demonstrating the straight versus the double swept design. So here I'm going to play this clip for the straight bladed design. Then here's the double swept design. And so here you can, hopefully you will hear that, and you can tell that the double swept design is certainly quieter and softer than the straight bladed design. So our optimal rotor design, here's the parameters, and as I said, we did about 270,000 cases in this parameter optimization effort. So as I mentioned, we use Helios for simulating the CFD, for CFD simulations, and let me see if I can play this short movie for you, which basically just shows the flow field of the coaxial rotor system. Yeah, and hopefully you can see that CFD flow field result there. And so we used CFD to verify our BEMT predictions for the hovering flight case. Here you can see in this plot power for a series of collective angles and then thrust for a series of collective angles as well. You can see that we get pretty good agreement between the two within about 15% of each other. So we were pretty happy with that result. We also did a similar verification for the forward flight case. And so here's a short video showing the flow field structures in the forward flight case. And here you can see some of the vortices shed from the coaxial rotor system as well as the body itself. And so then we use those results to verify our BMT for the forward flight case. And that's demonstrated here in power versus forward speed for the BMT results, and then the discrete points with the CFD. And we even got better agreement here within about 10% of each other. So we were pretty happy with that. We weren't satisfied though. We wanted to take that one step further and do some experimental verification. So we did some rotor blade measurements on our subscale rotor using an in-house hover stand. And here you can see the power and thrust results with the BEMT, the experimental results, and the CFD, and we got good agreement all within 10% of each other. So this demonstrated that our acoustic predictions for our subscale were good, but we wanted to answer the question, do these hold for the full scale as well? And so we did an aerodynamic similarity study in which we used CFD results to examine the scalability of the aerodynamics. And that's plotted here in coefficient of thrust versus coefficient of power. And you can see that for both models, the full scale and the 1/3 scale, we get pretty similar results. Here are some of the non-dimensional aerodynamic parameters as well. And these were all pretty similar. So we were pretty confident that our full scale acoustic predictions would be accurate. And so that's what we did. We used our CFD predicted blade loads to simulate the noise in hovering flight. And so here you can see in this plot of the third octave analysis of the maximum noise level with the 4 key helicopter noise generation mechanisms, and then the directivity polar plot. There's a lot of interesting stuff going on here, a lot we could talk about, but the take home is that our predicted noise was about 70 dB at 50 feet. And we'll see later on how this compares with the actual flying aircraft. So we wanted to somehow verify these acoustic predictions. So we took our subscale rotor sound pressure level measurements and we scaled them up to the full scale size. And that you can see here in this sound pressure level versus frequency of our analysis, our predictions, and then our scaled experiments, and we got pretty similar results. So we were pretty confident that our full scale predictions would be accurate as well. And then here's a photograph showing the full scale rotor on the aircraft in the hangar. Now, as far as the blades themselves, they were manufactured with a foam core, carbon fiber skin, and a fiberglass reinforcement root. And here you can see various steps within that manufacturing process. All right, so let's talk about the electric powertrain now. So we had a few key requirements. One was a quiet all-electric propulsion system. We wanted a high torque, low-speed drive motor, and we tried to use lightweight aerospace-grade COTS parts where possible. And so I'll discuss the selection and testing of the motor and inverter, the development of the high-voltage battery pack, and then the development of a quiet one-stage transmission. So when it came to selecting the motor, there were a few options available, architecture options available. One was a radial flux stator. In this case, the magnetic lines of flux are perpendicular to the axis of rotation. On the other hand, you get axial flux stator, in which the magnetic lines of flux are parallel to the axis of rotation. And so we did a trade study of available radial and axial flux motors, and we determined that we get more torque per unit mass with the axial flux stator. And so we selected the MRAX 208 axial flux permanent magnet motor, had a mass of about 20 pounds, max continuous power of 55 horsepower. We selected the high voltage model for efficiency, and then this motor was an air-cooled model. And so what we did was we put this on a dynamometer and we tested it at our operating conditions. And so here you can see the motor, you can see our motor controller was the Cascadia Motion PM100DZ controller. And of course, it's attached here to the dynamometer. And so here you can see in this plot of some of our test data of torque versus RPM with the efficiency curves provided by the manufacturer. This here is our case for axial climb, for hover, and then also for forward flight. And so you can see that in all these cases, our motor efficiency was predicted to be over 94% for all these flight conditions. So that was the good part. The unfortunate thing, though, was that we experienced a lot of motor overheating during these testing. And that was partly due to the lack of sufficient cooling, lack of airflow over the motor. So what we did was we graduated to the next size MRAX motor, the 228. It was slightly heavier at 27 pounds, at a max continuous power of 83 horsepower. Again, we selected the high voltage, and the key was that this was both an air and water cooled unit. So these were the motors that we finally installed on the aircraft, one per rotor, and we also developed some custom cooling systems for each of the motors and inverters that kept it cool with a water cooled system. So as far as the battery chemistries, we considered a variety. We selected lithium because this gave us the highest energy density and comes in a compact pouch-based design. And so you can see in this spider graph of various performance metrics of batteries, we have a few different varieties shown here. In red is the lithium cobalt. It has a high specific energy but tends to overheat. And there's also lithium ion phosphate, which has a high specific power, and it has more thermal stability as well. And then there's other more exotic ones like the lithium manganese nickel cobalt. This is becoming used more in eVTOL applications. And so we finally selected a lithium ion pouch-based custom battery. This provided us with a high specific power. And here you can see in this photograph of the assembled battery pack, the specifications for this, it was 144 series wired 4 parallel cells, and it provided 11 kilowatt hours of battery. The peak voltage was 604 volts and had a mass of 200 pounds. So as you can see, there's a battery management system strapped to the back of this. This monitored all the individual cell voltages, the pack voltage and current, as well as 6 temperature probes that were dispersed throughout the pack. And so our pack level energy density was about 133 watt hours per kilogram. Now, as I mentioned, we had a one-stage reduction drive to meet the low RPM, high torque demands of our rotor, and we considered a few different drive styles, for example, belt and pulley. These have been demonstrated in a V-belt transmission in the YL-3A Quiet Star, which is a almost virtually silent aircraft developed during the Vietnam era. This, however, is not a particularly compact solution. Belts can suffer from runout noise. It requires a lot of heavy support structure. And then meshing noise can also be an issue with timing belts. So we also looked at chains and sprockets. Now this is a little more compact. You can mitigate the noise with a tensioner, but it tends to be maintenance intensive, mechanically complex, and also requires a heavy support structure. So we looked then at gearbox option. This is a more simple, elegant, compact, and reliable solution. It can, however, be relatively noisy. There are some steps you can take, however, to mitigate this noise. You can use, for example, you can use helical teeth, high contact ratio tooth profile. You can enclose the gearbox in a properly designed transmission housing and also provide with sufficient lubrication. And so this was ultimately the option that we went with. And so here's some photographs showing the pinion and wheel gear. These are a helical gear pair. Utilizes a custom high contact ratio tooth profile. It provides a 3.6 to 1 gear ratio and are manufactured of 9310 aircraft grade steel. And here you can see a photograph with the transmission housing around it. It was made of nylon 12 GF and filled with molybdenum grease. And pretty happy to report that this custom designed transmission was quieter than even the rotor during operation. So we were pretty happy about that. All right, so let's talk about the flight dynamics and control of the system. So in our system, we have dual rigid rotors. They are controlled with mechanically independent, electronically coupled swash plates. This gives us excellent control authority, maneuverability, and gust tolerance. And so here's a photograph showing the 1/3 scale rotor head, and here's the full scale rotor head. You can see some similarities between the two. Here are the top swash plates, the bottom swash plates, and the actuators that control them. Of course, the actuators were controlled by the flight controller, which processed feedback and pilot commands as well. And I have a video here showing the motion of the swash plate. Yeah, and here the pilot is just providing some inputs to the swash plates, and you can see the blades pitching in response. Yeah, so then as far as the flight controller itself, we used a custom designed flight controller with triaxial gyros and accelerometers, bidirectional communication, and it incorporated a tuned PID feedback loop that's kind of illustrated right here, where there's an inner loop for PID control and then outer loop for pilot commands. And I will say that initially we did use the Invention Verante autopilot on the full scale, but it proved unreliable for flight control, but we did retain it for cam communication and other subsystem control. So we modeled the flight dynamics of the system in order to predict the flight characteristics, evaluate its stability, and so we derived the fully nonlinear equations of motion. We got the inertias and mass from our CAD model. For the forces and moments, we used our BMT model with a Peters inflow, and all of this was analyzed using Texas A&M University rotorcraft analysis code. So we took our nonlinear system and we linearized it about hover and forward flight at 47 knots and stabilized it using a linear quadratic regulator. And here you can see the open loop and closed loop poles for the hovering case. You can see that it stabilizes all the unstable modes. And similarly for the forward flight model. And so this demonstrated that our linear feedback was in fact able to stabilize the unstable modes. Now we also did some flight simulations as well. The first thing was we perturbed it with a 15-knot upwind gust. And here you can see that the disturbance was regulated within about 15 seconds or so. And then we also simulated the entire competition course. So this involved vertical flight, forward flight, maneuvering flight, and all that stuff. And all of this demonstrated that at least predicted that our aircraft could handle gusts well and also perform well in tracking. Now we also did an X-plane simulation of the aircraft. Let me see if I can play this. All right, so this is a real-time simulation of our aircraft in X-plane. This was flown by an experienced helicopter pilot, and he reported that the aircraft behaved well. There were no unexpected dynamics or anything like that. So we were pretty happy with this result. Okay, so let's talk about the structural design and analysis of some of the parts in the aircraft, starting with the landing gear. Here you can see it has skids and vertical struts that convey the forces from the skids to the base plate. And one critical component is the cross tube. And so this basically acts as a leaf spring or a shock absorber to absorb the landing impacts. And so we used ANSYS finite element analysis to model it with a 1G and a 4G loading case. Here's our setup in ANSYS with the weight of the aircraft on the landing skids, and then the weight of the battery applied to the attachment points. And for the 1G case, here you can see the von Mises stress. Here's the case for the 4G loading case. And even under the 4G loading, you can see that the von Mises stress was below the maximum yield stress. So we were pretty happy with that. And interestingly, we did have a pretty hard landing. And here you can see some plastic deformation of that cross tube, which demonstrated its action of absorbing those landing impacts. And then here you can see the stresses for the rotor hub and the transmission support structure. And these are just examples of how we used FEA extensively to design all of these structurally critical members. All right, so let's talk about vehicle testing. We'll talk first about the 1/3 scale aircraft. Here you can see in this photograph on the right of the assembled aircraft, it had a gross takeoff weight of 22 pounds. And the first step of the testing was gimbal stand testing. This was to basically evaluate the system, figure out how it's going to respond to inputs and stuff. And so here you can see the rotor system It's mounted to the gimbal with a spherical joint and some counterweights to bring the CG to that spherical joint. And we had it mounted in a 3x4 foot wind tunnel for forward flight testing. All right, so here's a video of the rotor head testing in the wind tunnel. Pilot is providing, roll inputs, yaw inputs, pitch inputs, and there were no unexpected dynamics. So that was a really good result of this testing. Okay, so the next phase of testing was indoor tether testing for the subscale. This was to tune the flight controller and trim the rotors and stuff, and it performed well, and it was demonstrated stable flight. So that was a good result from that. Yep. So here is some indoor free flight testing. This was the next phase of the testing, and it demonstrated all the flight capabilities that we were expecting. It performed very well, and we actually used this video documentation as part of our phase 2 submission, proof of aircraft operation. So the fourth phase of testing was outdoor free flight testing. Yeah, so this was the fourth phase of testing. This was to basically demonstrate forward flight capability, demonstrate maneuverability and controllability in high-speed forward flight. And we were pretty happy with the performance of the aircraft. That rigid rotor system really turned out to have a lot of control authority, and of course in the hands of an experienced RC pilot that helped a lot. Okay, and then we also did do some sound pressure level measurements of our system in comparison with a thrust matched quad rotor. And let me show that here in this video, where we'll just listen in and hear the difference between the quad rotor in comparison to our system. And so here you can clearly tell that there's a marked difference between the two. And then here's some of the results from that testing, sound pressure level versus frequency for the two systems. And our system was about 18 dB quieter than that of the quad rotor. We also looked at efficiency as well. We experimentally measured the power and thrust for the two systems and found that the quad rotor required nearly 55% more power. So not only was our system quieter, but it was also a lot more efficient as well. All right, so let's talk about testing the full-scale vehicle. So here is a photograph of the assembled aircraft. Weighed about 550 pounds, empty weight, and could carry a payload of about 200 pounds. So the first phase of testing, as with the subscale, was gimbal stand testing. All right, so here we're doing the gimbal testing with the full-scale aircraft, and pilot is just giving some inputs. And as with the subscale, it behaved very well, very favorably. There was no unexpected dynamics, so we were pretty happy with that and gave us confidence to do tether testing. And so here we are doing some indoor tether testing with the full-scale aircraft. The pilot is providing some different inputs, and it responded favorably. And I'll note here the tethers are just for safety. They're not actually affecting the dynamics of the vehicle at all. And then from that, we collected some of the flight test data. This is the pitch and roll desired and measured rates. And the reason why these are important is because our flight controller was tuned by using these rates and angles. And we got pretty good agreement between the two of them, demonstrating that our flight controller is pretty well tuned. And there is a little bit more noise in the measured result, which is kind of expected for the rotary system. Now, during tethered indoor flight testing, we did do a hover endurance test, which lasted about 8 minutes. And here's some of the telemetry data from that. And we actually monitored this telemetry in real time and for all of the flight testing. So this helped us to basically evaluate the state of the aircraft at all times. Now, during indoor tether testing, we also did a payload test. And so we've loaded it up with 165 pounds of payload, and the aircraft lifted it very well. There were no issues, no unexpected dynamics, nothing really changed with the system. All right, and so the next phase of the testing was outdoor tether testing, and this basically allowed us to have an intermediate stage between indoor tethered and free flight outdoor. Another thing we did also was we measured the sound pressure level at 50 feet during this test. So let's play this here. So here we can see hovering at 50 feet, we're getting about 73 dBA or so, which is pretty remarkable for this size aircraft. In fact, as far as we know, this is the quietest aircraft in this weight category, the quietest rotorcraft in this weighted category that we know of. All right, and then the final phase of testing was outdoor free flight testing. And this, of course, was to demonstrate the forward flight capabilities of the system. All right, so here is the outdoor free flight testing of the full-scale aircraft, and it performed pretty well. It handled very smoothly. Here you can see the pilot just doing some back and forth laps over the tarmac. Unfortunately, it ended up crashing, so we weren't able to demonstrate it in the final fly-off, but we were pretty happy with the way it performed here. Okay. So with that, we'll summarize briefly. So Team Harmony, we designed and developed and flight tested both a subscale and a full-scale ultra-quiet coaxial helicopter personal air vehicle as part of this competition. We were, of course, phase 1 and phase 2 winners, and some of the key innovations in this project included developing ultra-quiet and efficient rotor systems, using rigid rotors with independent collective and cyclic control, implementing electronically coupled dual swash plates for mechanical simplicity. And then, of course, we developed a custom electric powertrain and custom transmission, ultra quiet transmission, and then developed 11 kilowatt hour custom battery pack. And the key thing here is that our team designed, built, and flight tested a full scale aircraft in a mere 10 months. So this speaks to the dedication and commitment to our team. So some of the key takeaways, some of the lessons learned. So we demonstrated first that it is possible to significantly quiet rotors without losing efficiency. Specifically, we measured 73 dBA at 50 feet, which is pretty remarkable. And we were able to achieve this through tip speed reduction, planform shaping, and acoustically tailoring the blade design. Another thing we saw is that endurance really is still a serious limitation for eVTOL aircraft. We were able to meet the size and the noise constraints, most likely the speed constraint as well, but definitely not endurance. In fact, our longest hovering flight, as I mentioned, was only 8 minutes. That was from full charge to almost completely depleted, and that was with no payload. So this really just speaks to the low energy density of current battery technology. We were only about 133 watt hours per kilogram at the pack level. Also, there is a need for reliable, lightweight aerospace grade COTS parts specifically for eVTOL applications. We had numerous mechanical and electrical issues. Some of these were expected just as a process of developing the aircraft. But some of the COTS parts were pretty heavy. For example, the motor controller, some of them were unreliable, the first autopilot that we tried. And so these are some of the key results from this study. So the question is, what's next? Well, we are still pursuing the GoFly prize. There's no winners yet. It's still an ongoing competition. So if we can at any moment demonstrate that we have an aircraft, then that prize is up for grabs. Now we did start a company, a small business, Harmony Aeronautics, as a result of some of the IP that we have developed. And this is specifically focused on ultra quiet rotor technology in general application for eVTOL aircraft. And so Harmony Aeronautics, we won a phase 1 Air Force Agility Prime STTR grant. This was through the AFWERX program. And this was a 6-month, 150K feasibility study on developing these ultra quiet rotors for eVTOL and UAMs. And so we were fortunate, we got an MOU signed and we submitted a phase 2 proposal. And so we are currently awaiting those results. And they should be coming out here in a few minutes. We're biting our nails, just waiting for that. result. But if we do get that, then we'll be full steam ahead on this endeavor. So I know that was long. I thank you so much for your attention. And if you have any questions, be more than happy to answer them.
David, thank you so much for this talk. This has been really, really incredible. I didn't realize that it was, 10 months between all of these things. And so the progress and the work that you and your team put in has been like really amazing to see. I am going to go ahead and, since we don't have too many people, I'm going to go ahead and allow everybody, if you would like to ask questions out loud. I didn't see really any pop up in the chat box.
Brad Roberts actually submitted one, but probably best if Brad, if you can unmute and.
It was hiding from me. Yeah, Brad, if you want to unmute yourself, you should be able to now. Feel free to go ahead and ask that question of yours.
Did that work? Can you hear me?
We can hear you.
Hey, amazing. Okay, 2 questions that I observed. If you can help me answer it. What's the blade root radius cutout percentage? It looks like about 40%. And did your 9 degrees twist that you settled on, was that from the blade root airfoil at that 40% to the tip?
Yes, I believe the root cutout, I think, was around, like 35 to 40%. Yeah, and then the minus 9 degrees was from from that root airfoil all the way to the tip airfoil. So that would have been total of minus 9 degrees of twist.
Okay, great. Yeah, that sounded a little low for the hole diameter. If you carried that linear twist to the center of radius, then it would have been a little more on the what I'm used to type of twist arrangements. So that's cool. And then the second question was, you kind of went through pretty fast. I didn't catch everything, but it seems like you only got about 8 to 10 minutes out of your batteries. Is there anything?
Yeah, that's the maximum.
Yeah. How do you have to wait for battery technology to catch up in order to get your 30 minutes or 20 minutes?
Yeah, I mean, I guess if you're going to go with a fully electric system, then there's going to have to be some significant improvements, I think, in battery technology. Definitely. I mean, you're needing at least twice that in terms of endurance. So you will gain some, in forward flight, for example. The competition, the 20 minutes of endurance, right? That was forward flight at about 30 knots or so for the majority of that time. So we would have seen a little bit of improvement, right, if we had done some forward flight testing. But this was all in hover. So I don't know what that would convert to in terms of hover time, but certainly I wouldn't expect that 8 minutes of hover time would convert to 20 minutes of forward flight time. I would say batteries are definitely a significant limitation. Now, the batteries that we used were actually, they were custom built, custom assembled by an electric drag racer from Houston. And so he has experience making very high power output batteries for, high acceleration and in his drag racing operation. So he had of all the research that we had done, he had the highest watt hours per kilogram available. So he didn't tell us exactly, what his kind of secret sauce was or what the specifics of the battery chemistry were, but that was about the best that we could find. And that was even better, I think, than, like CoCam cells, for example. I know CoCam cells are used a lot in electric aircraft as well, but we found that this guy's batteries were actually outperforming those. So I think battery technology, that's key, man.
Yeah. Are you thinking about any hybrid in order to win the prize, or are are you restricted to electric only? I don't know.
We have seriously considered it. And in fact, we're actually developing a scaled version 2 of the GoFly vehicle, and it's going to have a gasoline engine or some sort of hybrid configuration. I think at this point there may be enough efforts you can put in to mitigate the sound of a gasoline-based engine, so that it will be louder. It won't be as quiet as electric, but maybe it'll still be under the competition limitations. It's kind of what we're hoping for. But certainly for the endurance, you're going to need at least some sort of hybrid system or something. So yeah, we'll just have to see if we can put in the necessary noise mitigation strategies for quieting the gasoline-based engine. So.
All right, David, I've got a question for you.
Yeah.
It involves the pilot. I feel like we kind of glossed over it. So what was the reasoning behind the choice for putting the pilot above the rotor system as opposed to below? My initial thought is, any kind of movement by the pilot, or if you have a heavier person above, that's going to really kind of mess with your stability. So I was curious about why you guys put the person above versus below.
Yeah, so that was really as a result of the competition constraints. Because as I had mentioned, they really encourage this kind of clear field of view, right? It's like this flying experience, right, was kind of what they were going for. So they didn't want anything to obstruct the field of view of the operator, of the pilot, and they considered in the competition, spinning, rotating rotors to be opaque structures. So this was something that, so they really disincentivized any kind of overhead rotors, because they consider, oh, that's an obstruction to your field of view. So we're like, well, your only option then, is to stick them in on top, right? Which, there's obviously other questions that brings, right? But at least in that sense, then you have a clear field of view, in all respects. Now, one thing I would say about the weight distribution, right? So they said you got to put a pilot or an equivalent 200-pound payload above it, right? And that really fit quite nicely with our battery pack, which was 200 pounds underneath the system, right? So you have like 200 pounds up here and then 200 pounds down here, and that puts your CG like almost right in the middle of your rotor system, which is kind of nice. So we didn't really see that as a problem, right? Having the payload up there, that really wasn't a problem, because we had that the big battery weight underneath. So yeah, so that was kind of the rationale behind that thinking and stuff. So.
Gotcha. That was my other question. Was there a weight limit to the pilot? Is there a certain person that you're trying to thinking of putting up there? So that 200 pounds answers that for me. Thanks.
Yeah, that was kind of the 95 percentile, something like that. So GoFly said, okay, it's got to be 200 pound person or equivalent. So yeah, I guess if you're over 200 pounds, you can't fly it. And then if you're under 200 pounds, you got to add weight to make yourself 200 pounds. So
I was going to say, it looks like George DeVore, one of our attendees, has his hand raised. George, if you want to unmute yourself and ask your question.
Yes. I was going to ask if you designed any redundancy in the system for emergencies.
You mean in terms of you mean like structural or rotor based or electrical, or just anything, I guess?
Yeah, just any kind of redundancy, like possibly the actuators for the swash plate. If one of those failed, what would happen?
Yeah, so I know that we considered getting the redundant actuators. I don't remember if the actual actuators we had were redundant or not. I don't think they were. Yeah, so those were not redundant. Let me see. We had what else do we have? We had two data links. I know between the two different flight controllers. I think we had yeah, there was a backup data link for telemetry. But I think other than that, I don't think there were really any redundant systems. It's pretty heavy as it was. So
Yeah, I would imagine.
that would be something I think. Yeah, I think for a production vehicle, yeah, you definitely want some redundancy in there, and yeah, we would perhaps think about that and incorporating that in our next design. So.
Well, I appreciate your answer, and very impressive. Everything was awesome to see.
Yeah, thanks for listening, and getting more questions, let me know.
Mobile, any comments from you as David's now former advisor? I guess you're never outside of that advisor role, but now that he's graduated, he's more of your business partner.
No, I think Dave did a great job of explaining everything. No additional comments from my side.
Excellent, David. That means you did a great job.
Yeah, well, we've been through this presentation a time or two, so it's not like this is the first rodeo. So yeah, I've had the opportunity to present this work to other guys and government contract folks and stuff like that. So it's really been really been an opportunity, really been a privilege. So yeah, it's been great working on the project, and we were out at the hangar not long ago, and I was there with Mobile and some other guys and another committee member of mine, and I was like, oh, so this was before I started writing my dissertation. I was like, oh, so what are we gonna do about GoFly? And Mo was like, you need to worry about writing your dissertation first. So I'll be more than happy to work on building another helicopter.
So Elizabeth, I want to add one thing though. It's a lot of, like David mentioned, there's a lot of commitment from the students, right? This would not have been possible, without the 16-hour, 18-hour days these guys spent in a cold, hot hangar, right? So we were working off a hangar near the,
right.
Yeah. So it's getting this thing done in 10 months it's not a trivial task, right? And the other thing is, like, all the graduate students, right, they were doing this outside of their regular research, right? So they're trying to find time, and which has delayed their graduation and so on. So it's a lot of commitment from 5, 6 students from A&M. They work day and night to make it. So a lot of credit to them.
As a graduate of the human-powered helicopter team, I understand that commitment.
I used to, so Elizabeth, I used to talk about that all the time. I said, there's students like Elizabeth, Ben, Barry, Graham, I used to bring you guys up all the time. These guys work so hard on the human-powered helicopter.
Well, you learned from the best, Mobile, obviously. David, your roots started the best as a Maryland student. I'm a little
it's that Maryland heritage. It just runs in your blood, in your veins.
Yeah, I mean, it's a great learning experience for the students, right? I mean, you're doing all this. You're designing. You're not just designing, not just a paper design, right? You're actually building this vehicle, and we have seen this, and in the end, the vehicle crashed a week before the GoFly, right? Heartbreaking for us, right? So exactly a week before we had planned to go to California, we had a flight test, and the vehicle just turned over, like it crashed, it rolled over and crashed.
Oh,
and
no!
Breaking after all this work everybody put into it. So I think it's now when we fly a small drone, we don't even nothing makes us nervous. Everybody's strong, and I think it's an invaluable experience for the students to be part of something like this, when they're in grad school, like
Absolutely.
The flight test, the full-scale helicopter. Hard to beat an experience like that. Yeah, we're all very happy, even though we spend a lot of time. We're very, very happy about this. We'll go back and do it again.
Excellent.
With some design improvements.
Of course. Okay, with that, I don't want to keep anybody too late. We are a little bit over what we said, but I think this was a really, really fascinating talk. Again, I want to thank everybody for joining us today. If you want to check out this video again, if you want to see some of what David was talking about, this will be posted after some editing to YouTube. Feel free to reach out to me if you are curious about that link. I added both my work and my personal email in the chat box. Again, if you also have any questions for David and you want me to pass those along, I'll let him reach back out to you after you send them to me. For those who are VFS Southwest members, again, there's a reminder that the Licton competition that we have, oh no, my computer's about to die. November 19th or when those papers are due. And with that, I want to say good night and thank you guys so much. David, again, thank you, and congratulations on your doctorate and all of the success you guys have had with this project.
Thank you. Thank you for all your hard work too. Appreciate it.